Welcome back, everybody. Today we need to make a distinction between some terms in electricity and electrostatics that are really similar terms and related meanings, but definitely separate meanings. Now this gets confusing because those terms are so close together. So the three terms that I want to address first, and there's two more we'll add to this in just a minute, are electric potential energy, electric potential, and potential difference. You see what I mean about the terms being confusing? They all sound really similar. And so when you're reading a question, it's really important that we read so carefully to know exactly what we're asked to find in these problems. First off, electric potential energy. It's an energy type, just like we've solved for with gravitational potential energy or elastic potential energy. This is electric potential energy. So it's potential energy, which means energy of position or condition. So in this case, it's position relative to electric charges. We're going to use a capital U for the sign on this and a subscript E for electric, so electric potential energy. The units on this are joules, and we have an equation for electric potential energy, and that equation has the 1 over 4 pi epsilon naught again, so we've seen that quite a few times. Keep in mind that your equation sheet has a value for this whole quantity, 1 over 4 pi epsilon naught. They call that the K value, and what do they label that? The Coulomb's law constant is this whole thing. So you don't need to plug in the 4 pi and the epsilon naught, just use the value that they give for that whole fraction. And then multiply it by the product of the two charges. So bigger charges will have more potential energy than smaller ones. That makes sense. And divide that by the distance between them. Not the distance squared, just the distance between them. So we got to keep our eyes out for when these denominators are squared and when they're not. Force was exactly the same equation, just without the square in the bottom, which makes sense because force times distance is equal to work, which is equal to how much energy changes. So if we took that force equation, which was this one with a square, multiply it by the distance, which is r, then one factor of r cancels out, and the work we do, or the amount of energy change, is given by this expression. So that's energy. Energy is a scalar quantity, not a vector. That is true for all three of these, in fact. None of these are vector quantities. So at least, even if we have the more confusing terminology here, we don't have to deal with vector addition on these problems. So that's one nice thing about these. Next up, we have electric potential. We've dropped the energy from the term here. So not electric potential energy, electric potential. We looked at electric field and gravitational field, and we thought of those as ratios between the force and the charge for electric field, or between the force and the mass for gravitational field. Electric potential is going to be kind of similar to that. It's a ratio of the electric potential energy to the charge. So we might say that a certain location has a certain value of electric potential, and then if we put a charge there, that charge we could figure out very easily how much potential energy it has just from its position. Now the units on this are joules per coulomb, because it's energy divided by charge, so joules per coulomb, or we abbreviate that with a capital V and we call it volts, which leads into our other confusing terminology, volts versus voltage. We'll come back to that one in just a minute. So if we were looking at a single point charge, just somewhere in space, and we looked at some other location near that charge, and we wanted to figure out what the electric potential at that point would be, so that later on we could say, okay, well now we know that we have some charge that we're going to put in there, and we can very quickly figure out what the potential energy would be at that location. We're just going to take the expression we had earlier for UE, the electric potential energy, right here, and we'll divide it by Q. And it doesn't really matter which Q we're talking about here. There's only going to be one left, so we'll just call that Q, no subscript anymore. So this charge is whatever charge is causing that electric field that leads to our electric potential, and if we put a second charged object there, that would lead to our electric potential energy. If we have multiple charges, we can just add up the electric potentials from each charge. So if we had, say, a positive charge here and a negative charge here, and we wanted to know what's the electric potential right here, well, we'd figure out the electric potential from this one, and we'd figure out the electric potential from this one, just using this equation that we were looking at earlier, and just add them together. So that's just a mathematical way of representing that. The 1 over 4 pi epsilon naught, that's a constant, so we can factor that out of every term. And then this is just saying add together all the different Q over R terms that are involved in this problem. So the charge for this divided by this distance, plus the charge for this divided by this distance, add those together, and then multiply by 1 over 4 pi epsilon naught, and we get our total potential difference. Sorry, total electric potential. You see, I already made that mistake. Potential difference is our next one. So electric potential, very closely tied with electric potential energy. It's the ratio of this value to the charge of some object that we would put in there. Next up, potential difference. This one at least makes sense with the difference. It's the difference in electric potential for two positions. So you might call this electric potential difference. Usually we just say potential difference. We drop the electric there. So we write this one out as a delta V, the change in electric potential. We still use the same units, joules per coulomb or volts. The equation for this is just the electric potential between 2 points. The potential difference between 2 points. I did it again. Potential difference between 2 points is just the electric potential at one point minus the electric potential at the other point. One more bit of confusion, just in case we didn't have enough here, is that electric potential is often called voltage. So we have the voltage, which is measured in volts, though this quantity, which is measured in volts, is not called voltage. A little confusing. Oh, okay, a lot confusing. Super confusing. That's why you gotta spend some time getting these things straight, wrapping your head around the different definitions. Get familiar with each of the calculations and each of the units that you use with these. We're going to be careful to try and avoid calling this voltage as much as possible. Even when we talk about batteries, batteries are labeled with their voltage on the side, but we're going to be sure to call that the electric potential difference or just the potential difference as much as possible to try and avoid confusion there. But we got to face the facts that we might see voltage describing something in a problem that we come across. So we need to know that voltage really just means potential difference. So let's try a calculation of potential difference, which kind of incorporates these other two here. Electric potential energy is pretty straightforward. It is worth noting that this can have positive or negative values. If we have two positives or two negatives, we'll have a positive electric potential. But if we have one negative and one positive, that'll be a negative electric potential energy. Remember, though, with gravitational potential energy and with elastic potential energy, we very rarely cared what the value at any certain point was. We were really more interested in how much that value changed by. So this may give us kind of weird answers for electric potential energy for a single position, but the change in potential energy will make sense to us as we're going. So if we, say, have two positive charges that are very close together and then they spread farther apart, electric potential energy is decreasing as they do that, which makes sense. It's like falling down a hill. It's the direction the force is pushing you. As you go in that direction, your potential energy decreases. You have less potential for movement, for action. Okay, so we've got three charges here that we're interested in. We want to find the potential difference from point A to point B. So the potential difference is just electric potential of each of these points, and we'll do a subtraction. And if we want the difference from point A to point B, we're just going to do delta V is equal to VB minus VA. just like if you wanted to figure out what's your difference in money between these two moments where you have $5 and then you have $10, well, we would give a positive $5 as our answer. We took the 10 minus the 5, the ending point minus the starting point here. So delta V is VB minus VA. All right, so now we need to calculate each of these values, VB and VA. Let's start with B. VB equals, don't do any vector signs here, these are scalar quantities. VB equals, and equal sign is going crazy. Okay, so our overall equation, 1 over 4 pi epsilon naught times, and then we're going to add all the charge over distance fractions together here. So we've got, let's see, 5.0 microcoulombs is times 10 to the negative 6th coulombs, divided by our distance to point B is 1.0 meters, plus, let's see, a negative 2.5 times 10 to the negative 6th coulombs, divided by the distance to that Q3 here is also 1 meter, plus our last charge, 3.0 times 10 to the negative 6th coulombs, divided by this distance right here, so we'll just do a little Pythagorean theorem. So this is 1 meter, this is 1 meter, so 1 squared plus 1 squared is 2. That's equal to the square of this distance, so that'd be the square root of 2 meters. Okay, and then when we plug this into to our calculators, keep in mind that 1 over 4 pi epsilon naught, that whole quantity has, that whole fraction has a value given in the on the equation sheet, and that is 9.0 times 10 to the 9th Newton meters squared per coulomb squared. Okay, and then over here, let's see, we've got 5 times 10 to the negative 6 divided by 1, so that'll be 5 times 10 to the negative 6th coulombs per meter, minus 2.5 times 10 to the negative 6th coulombs per meter, plus, and then 3 divided by the square root of 2 times 10 to the negative 6th coulombs per meter. Okay, so VB is going to be, and I'm just going to type all this in at once, let's see, 9 times 10 to the 9th times parentheses 5 times 10 to the negative 6th minus 2.5 times 10 to the negative 6. I should have just done overall 2.5 times 10 to the negative 6. Oh well, plus 3 over square root of 2, and that is, oops, plus 3 divided by, not to the power of, okay, 3 over square root of 2, and that's also times 10 to the negative 6th. And let me just double check here. 5 times 10 to the negative 6, 2.5 times 10 to the negative 6, and 3 over square root 2 times 10 to the negative 6. Okay, so our potential at this point is 41,492, and that is, let's see, we got Newton meters, one factor of meters will cancel out there. Newton meters per coulomb, or Newton meters is the same as joules, so that's joules per coulomb, or we could call that volts. So 41,592 volts at that point. Next up we'll do VA, which is 1 over 4 pi epsilon naught times, okay, so we have a little bit more trig to do, it looks like here. Let me get a different color so we can tell the difference. Let's see, so each of these distances will be equal, since that's right at the middle of the square. We said that this whole distance was equal to the square root of 2 meters, so that must mean that this distance right here is the square root of 2 over 2 meters, which is the same as this distance and the same as this distance. So all of these are square root of 2 over 2 meters. Okay, so now we've got, let's see, that's 5.0 times 10 to the negative 6 coulombs divided by square root of 2 over 2 meters, plus a negative 2.5 times 10 to the negative 6 coulombs divided by square root of 2 over 2 meters, plus 3.0 times 10 to the negative 6 coulombs divided by square root of 2 over 2 meters, and end our parentheses. Okay, so now VA is equal to 9.0 times 10 to the 9th Newton meters squared per coulomb squared. I'm just going to factor out the square root of 2 over 2, so it's divided by square root of 2 over 2, so that's the same as multiplying by 2 over the square root of 2. That's meters on the bottom, and then that gets multiplied by, let's see, 5 minus 2.5 is 2.5, plus 3 is 5.5 times 10 to the negative 6th coulombs. So our voltage at point A, we got 9 times 10 to the 9th times 2 over square root of 2 times 5.5 times 10 to the negative 6th. Alright, and it looks like there we get 70,004 joules per coulomb, or again, volts. Alright, and I ended up making just a ridiculously high potential difference here, or potential difference, but that's okay. The numbers still work out just fine. So now delta V is going to be that, so what do we say? VB minus VA, so that'd be the 41,592 volts minus the 70,004 volts, and we get delta V. The potential difference then is equal to negative 28,000, I'll call it negative 28,400 volts, which is that's a pretty big potential difference there. That'd be a heck of a battery, but that's okay. We're dealing with extremely large charges here and placed pretty close together. Keep in mind that when we're talking charges, we usually mean, or we're usually dealing with very, very small numbers per charge. So even microcoulombs is a pretty big charge when we're talking about a distance like this. One last point here, and that is relating work done to charge, or work done on a charge, and determine how much work it takes to move a charge from one place to another, or how much the speed of that charge is going to change as it goes from one point to another. So we're using the definition for work that we've worked with before, that work is equal to change in energy. And in particular, the energy that we're looking at here is the electric potential energy. Okay, so if we have a given electric potential, or potential difference rather, if we have a given potential difference, we can figure out how much electric potential changes. That's what this value is. Potential difference is how much electric potential changes. All we have to do is multiply that by Q, by the charge, to figure out how much electric potential energy changes. So we'll know delta V. We also know that that the electric potential energy is equal to Q times the V. So if we want to find the change in electric potential energy, that would be Q times the change in V. That's just Q times the voltage, or times the potential difference. So work here is just going to be equal to Q times delta V. And that should be a capital V. I I'm not doing a very good job being consistent with my capital letters here. I got to be careful with that. Okay, so Q times delta V. Now over here we've got a potential difference between two plates on a capacitor is 9.0 volts. We've got, let's see, a distance between those, and let's see. I guess now that I think about it, that information actually isn't even necessary. I was thinking we were doing solving a different problem here, so we don't even need the distance there, but that's okay. We can just ignore that. How much work would be required to move an electron from the positive plate, not page, autocorrect, oh my goodness, and this is Ann. Wow, autocorrect is killing me on this, but what can you do? Okay, so we've got 9 volts of potential difference. We've got an electron which has a charge of, oh boy, what is the charge of an electron? Better go to that constants sheet that comes with your equation sheet. The charge of an electron is a negative 1.60 times 10 to the negative 19th coulombs. And we know our voltage, or our potential difference, is 9.0 volts. So the work is going to be equal to just Q times V, which is 1.60 times 10 to the negative 19th coulombs times 9.0. Volts, remember, is just short for joules per coulomb. So that'll be a good way to write that. So the coulombs cancel. And very simply now we get our work is equal to 1.6 times 10 to the negative 9th times 9. Let's see, 1.44 times 10 to the negative 8th joules. And the, let's see, the sign here really would be this direction, but since from the positive to the negative, this would also be the same sign. And so we really just need to think about, okay, does it take work to do this, or would it happen on its own? So if we're trying to get an electron to go away from positive and toward negative, we'd have to do work on the electron, so we'll call that positive work here. But very small amount of work, but it's also just for a single electron. So think about the huge numbers of electrons involved here, and we start to understand that, yeah, it would take a large amount of work to move very many electrons around, at least on the scale that we'll be dealing with when we get to electric circuits, which involve lots and lots and lots of electrons.